Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Tonight, we begin gently. There is no rush here. No engines to ignite, no countdowns, no pressure to understand everything at once. Only a quiet unfolding, like a map of the universe slowly spreading open beneath closed eyelids. For as long as human beings have looked upward, we have wondered how to reach the distant lights. Ancient sailors traced constellations across dark oceans. Early astronomers marked planetary motion with careful ink. Modern physicists write equations that describe the curvature of spacetime itself. The longing is the same, only the language changes. We look at the stars, and we ask how to travel there. And almost immediately, we encounter a boundary, the speed of light. In everyday experience, speed feels negotiable. A faster engine, a lighter material, a more powerful fuel, and we go a little quicker. But in the universe described by modern physics, the speed of light is not merely a practical limitation. It is structural. It is woven into the geometry of reality. Light does not simply move quickly. It defines how space and time relate to each other. And so faster-than-light travel feels impossible, not because we lack technology, but because the structure of space-time itself appears to forbid it. And yet, physics is a subtle discipline. It teaches us to distinguish between what seems impossible and what is geometrically prohibited. There is a difference between moving through space faster than light and shaping space itself. That difference is the doorway into our journey. If you imagine a small boat on a still pond, and the boat tries to move faster than the ripples it creates, there are constraints. But if the pond itself could stretch or contract, then distances would change, without the boat ever locally exceeding the speed of the water. In the language of general relativity, space is not a rigid stage. It is dynamic, flexible, responsive to mass and energy, and perhaps, under certain mathematical conditions, shapeable. This is where warp drives leave the realm of fiction and enter geometry. The phrase warp drive often carries cinematic imagery, brilliant flashes of light, stars streaking past in elongated lines, spacecraft leaping between galaxies in moments. But beneath those images, there is something quieter, a metric, an equation, a description of how space-time could be curved in a particular configuration. Miguel Alcubierre showed in 1994 that Einstein's equations of general relativity admit a solution in which space-time expands behind a region and contracts ahead of it. Inside that region, a spacecraft could remain locally at rest. It would not break the speed limit in its immediate surroundings. Instead, the geometry around it would move. This distinction is delicate, but essential. Objects cannot locally exceed the speed of light in vacuum. But space-time itself is not bound by that same rule. In cosmology, distant galaxies recede from us faster than light due to the expansion of the universe. This does not violate relativity because no object is outrunning light in its local neighborhood. Rather, the fabric between objects stretches. Warp drive physics emerges from this insight. It asks not how to accelerate a ship beyond light speed, but how to engineer space-time so that the destination moves closer. This idea is not engineering. It is mathematics, and mathematics in physics is a precise language. When we speak of a warp bubble, we mean a region of spacetime described by a particular metric tensor. When we speak of expansion and contraction, we mean specific terms in Einstein's field equations shaping curvature. When we speak of exotic energy, we mean stress-energy distributions that violate classical energy conditions. This is not fantasy, it is careful geometry, and yet it remains theoretical. There is no experimental warp engine, no laboratory generating macroscopic spacetime bubbles, no vessel resting inside a controlled curvature field. But there are equations, and equations are how physics dreams. Tonight, we will explore those dreams slowly. We will not rush ahead to engineering challenges. We will not leap immediately into speculation. Instead, we begin with the structure of reality itself. Because before warp drives, there is relativity. Before relativity, there is the speed of light. And before that, there is the human question. Why do we long to cross impossible distances? Perhaps because distance itself feels like a mystery. The nearest star beyond our sun is more than 4 light years away. A light year is the distance light travels in 1 year, roughly 9 trillion kilometers. Written out slowly, 9 trillion kilometers. Even the fastest spacecraft humanity has launched would require tens of thousands of years to reach that star. The scale is humbling, and humility is often where science begins. When we encounter limits, we learn their shape. Relativity teaches us that space and time are not separate. They are woven into spacetime. It teaches us that simultaneity depends on motion, that clocks tick at different rates depending on velocity. That lengths contract along the direction of travel. It teaches us that gravity is not a force pulling downward, but curvature guiding motion. These insights are not dramatic when spoken slowly. They are quiet revolutions. They reshape how we think about movement, distance, causality, and time itself. Warp drive research does not discard these principles. It builds upon them. The idea is not to break relativity. It is to ask whether relativity allows a geometry that appears to bypass its own limits, without violating them locally. This subtlety is what makes warp physics scientifically interesting. It is not about defiance. It is about interpretation. If space-time can bend around mass, could it bend in more elaborate ways? If the universe expanded faster than light during cosmic inflation, could local curvature configurations imitate that behavior? These questions are not casual. They are rooted in Einstein's equations, in stress-energy tensors, in causal structure. They involve concepts like light cones, time-like intervals, space-like separations. They require careful attention to how geometry defines what events can influence one another. And so, as you rest, allow the idea of space-time to soften in your mind, not as empty space, but as a 4-dimensional fabric, responsive to energy, shaped by matter, governed by geometry. Imagine distances not as fixed lines, but as dynamic relationships. Imagine that moving faster than light might not require outrunning photons, but instead reshaping the map. Physics studies ripples in this fabric. When a star collapses, space-time curves intensely. When 2 black holes merge, gravitational waves ripple outward. When the universe expands, the metric itself evolves. Warp drive research is an extension of this study. It is the exploration of extreme curvature configurations. Some configurations demand negative energy density. Some introduce horizons that isolate regions causally. Some challenge our understanding of quantum fields. And modern refinements, including the work of Dr. Harold Sonny White and more recent modular warp geometries, attempt to redistribute curvature in ways that may reduce theoretical energy requirements. Segmented nacelle configurations, multiple curvature regions arranged symmetrically, computational modeling of stress-energy distributions. These are not fantasies. They are ongoing mathematical investigations. Still theoretical, but precise. Tonight, we will explore all of it, slowly. From the foundation of special relativity, to the curvature of general relativity, to the Alcubierre metric, to modular refinements, to quantum vacuum constraints, to horizons and causality, to alternative models, to the limits of space-time itself. But for now, simply breathe. Let your thoughts move at the speed of light and then slower. Slower than photons crossing empty space, slower than galaxies drifting apart. Rest inside the geometry. Because before any ship can warp space, we must understand what space is. And that understanding begins gently with light. Let us begin with light. Not as brightness, not as warmth, not as something that illuminates a room, but as structure. In physics, the speed of light in vacuum, approximately 300,000 kilometers per second, is not simply a measured velocity. It is a conversion factor. It is the number that links space and time together into a single geometry. When Albert Einstein proposed his theory of special relativity in 1905, he began with 2 postulates. The first was simple. The laws of physics are the same in all inertial reference frames. An inertial frame is one that is not accelerating. If you are floating freely in deep space, drifting at constant velocity, and you perform an experiment, the results will be the same as for any other observer moving at constant velocity. There is no absolute state of rest. There is no preferred cosmic frame. The second postulate was more surprising. The speed of light in vacuum is the same for all inertial observers, regardless of their motion relative to the light source. Pause with that idea. If you chase a beam of light, you do not measure it to be moving more slowly. If light approaches you, you do not measure it to be moving faster. Its speed remains constant. This constancy forces a profound rethinking of space and time. Because if the speed of light is the same for everyone, then measurements of space and time must adjust to preserve that fact. Imagine two observers moving relative to one another. Each carries a clock. Each measures distances with rulers. If they both measure the same light pulse, and both find its speed identical, then their measurements of time and length cannot both remain unchanged. Time must dilate, lengths must contract. These are not illusions, they are geometric consequences. Time dilation means that a moving clock ticks more slowly relative to a stationary observer. Length contraction means that an object moving relative to you is shorter along the direction of motion. These effects are negligible at everyday speeds, but they become dramatic as velocity approaches the speed of light. The factor that governs these transformations is called the Lorentz factor. It depends on velocity divided by the speed of light. As velocity approaches light speed, the Lorentz factor grows without bound. Time stretches, length shrinks. Energy increases. This leads to another famous result, mass-energy equivalence. Energy equals mass multiplied by the speed of light squared. Written in words, energy equals mass times the speed of light multiplied by itself. Because the speed of light is such a large number, even a small amount of mass corresponds to enormous energy. But the same relationship implies something deeper. As an object with rest mass accelerates closer to light speed, its kinetic energy increases dramatically. To reach the speed of light would require infinite energy, and infinite energy is not physically attainable. Therefore, no object with rest mass can reach or exceed the speed of light through space. This is not a technological limitation. It is geometric. The geometry of spacetime forbids time-like objects from crossing into light-like motion. To understand this more calmly, we introduce the idea of spacetime. Before Einstein, space and time were separate arenas. After Einstein, they form a four-dimensional continuum. 3 dimensions of space, 1 dimension of time, unified. In this framework, events are described not only by where they occur, but when they occur. The interval between two events is not simply spatial distance, nor simply time difference, but a combination of both. This combination remains invariant across observers. It is called the space-time interval, and it defines the structure of causality. Imagine a point in space-time, representing an event. From that point extends a light cone. The light cone separates space-time into regions. Inside the cone are events that can be causally connected, events that can influence or be influenced by the original event through signals traveling at or below the speed of light. Outside the cone are events that are space-like separated. They cannot be causally connected without exceeding light speed. Time-like intervals correspond to events within the cone. Light-like intervals lie precisely on the surface of the cone. Space-like intervals lie outside it. This structure defines what can affect what. It defines cause and effect. If you could travel faster than light through space, you could move from one event to another that lies outside the light cone. Different observers would disagree on the ordering of those events. Causality could reverse, effects could precede causes, paradoxes would emerge. This is why faster-than-light motion through space is not merely fast, it is disruptive to the structure of reality. The speed of light is therefore not just a speed limit, it is the slope of the light cone. It is the angle that defines causal geometry. It is the conversion constant that tells spacetime how to blend meters and seconds into one invariant structure. And so, when we speak of warp drives, we must tread carefully. We cannot simply imagine a rocket engine pushing harder, because no matter how strong the engine, it cannot locally accelerate a mass beyond light speed. Instead, if there is a path forward, it must lie in geometry itself. Consider again the distinction between moving through space and shaping space. Special relativity governs local motion in flat spacetime, but general relativity extends this idea. It tells us that spacetime can curve, it can stretch, it can expand. In cosmology, we observe distant galaxies receding faster than light. Yet this does not violate special relativity, because those galaxies are not locally outrunning photons. The space between us and them is expanding. The metric that defines distance is evolving. The geometry itself changes. This distinction is subtle but essential. Locally, nothing outruns light. Globally, spacetime may expand in such a way that distances increase faster than light can traverse them. Warp drive concepts exploit this subtlety. They do not attempt to break the light cone locally. They attempt to modify the geometry so that the path between origin and destination is shortened or carried along by a moving curvature region. But before we explore those ideas, we must fully understand the foundation. The speed of light is not arbitrary. It arises naturally from the equations of electromagnetism. It appears in Maxwell's equations as the propagation speed of electromagnetic waves. When Einstein examined those equations, he recognized that their structure implied a universal invariant speed. Rather than assuming space and time were absolute, he allowed them to adjust. This shift from absolute time to relative simultaneity is one of the most profound changes in human thought. Two observers moving relative to one another will disagree about whether two distant events occurred at the same time. Simultaneity is not universal, it depends on motion. And this relativity of simultaneity ensures that causality remains preserved so long as no signal exceeds light speed locally. Thus, the speed of light defines the maximum speed of information transfer. It defines the causal order of the universe. It shapes the geometry of reality. When we say that warp drives cannot be about going faster than light locally, we are acknowledging this structure. They must instead involve space-time engineering, geometry rather than velocity, curvature rather than thrust. This insight completes our foundation. Special relativity tells us that local faster-than-light travel breaks causality. The speed of light is the invariant constant tying space and time together. Time dilation, length contraction, mass-energy equivalence, Lorentz transformations, light cones, time-like and space-like intervals. All of these emerge from the constancy of light speed, and they collectively form the boundary conditions within which any warp concept must operate. We cannot ignore them, we must build upon them. And now, having seen how the speed of light defines the shape of reality, we are ready to examine space-time itself more deeply. We continue gently, because the structure of reality deserves patience. We have spoken of the speed of light as a constant, as a boundary, as the slope of the light cone. But we must go deeper still. In special relativity, space and time are unified into what Hermann Minkowski described as a four-dimensional continuum. He once said that henceforth space by itself and time by itself would fade into shadows, and only a union of the two would preserve independent reality. This union is not metaphorical, it is mathematical. Every event in the universe can be assigned 4 coordinates, 3 for space and 1 for time. But these coordinates depend on the observer's state of motion. What remains invariant is the space-time interval. The interval between 2 events is calculated by combining the time separation and spatial separation in a precise way. Time separation squared multiplied by the speed of light squared, minus spatial distance squared. The result remains the same for all inertial observers. This invariant interval is the true measure of separation in spacetime. It replaces absolute distance. It replaces universal time. And from this interval arises the distinction between time-like, space-like, and light-like separations. If the interval is positive, the separation is time-like. One event can influence the other through slower-than-light motion. If the interval is 0, the separation is light-like. Only a light signal can connect them. If the interval is negative, the separation is space-like. No signal limited by light speed can bridge them. This classification defines causality. It defines the architecture of influence, and it ensures that causes precede effects in every observer's frame, provided that no information exceeds the speed of light locally. The geometry is not optional. It is enforced by the Lorentz transformations. These transformations describe how coordinates change between observers moving relative to one another. They mix space and time together. Time in one frame includes contributions from space in another. Space in one frame includes contributions from time in another. This mixing preserves the invariant interval, and it preserves the constancy of light speed. Imagine two observers, one at rest, one moving at a constant velocity. Each draws axes on a space-time diagram. The moving observer's axes tilt relative to the stationary observer's axes. But the light cone remains the same. Light always traces lines at 45 degrees in properly scaled diagrams. This invariance of the cone is the invariance of causality. Now consider what would happen if a massive object could exceed the speed of light. Its world line, the path it traces through space-time, would tilt outside the light cone. It would enter the space-like region. In some frames of reference, the ordering of events along that world line would reverse. Arrival would precede departure, effect would precede cause, closed causal loops would become possible. This is not merely counterintuitive. It is mathematically inconsistent with the structure defined by the invariant interval. Therefore, faster-than-light motion through space-time is not simply forbidden by energy constraints. It is forbidden by the geometry of space-time itself. Let us also address relativistic mass-energy equivalence more calmly. Energy equals mass times the speed of light squared. But mass in relativity is not simply weight. It is a measure of resistance to acceleration. As velocity increases, the kinetic energy required to further increase that velocity grows disproportionately. Near light speed, each additional increment of velocity demands dramatically more energy than the last. To reach light speed would require infinite kinetic energy. Infinite energy implies infinite stress on spacetime, and this is not physically realizable. Thus, nothing with non-zero rest mass can be accelerated to light speed through space. Photons, particles of light, travel at light speed precisely because they have zero rest mass. They follow light-like paths. They reside on the surface of the light cone. Massive particles reside within the cone. They move along time-like trajectories. This geometric classification cannot be bypassed by propulsion alone. This is the crucial realization. Warp drives cannot be engines that push harder. They cannot simply accelerate a ship beyond the light barrier. They must operate differently. They must alter the geometry in which motion occurs. And here we must carefully transition from special relativity to general relativity. Special relativity describes flat spacetime. It assumes no gravitational curvature. General relativity removes that assumption. It allows spacetime itself to curve in response to mass and energy. But before we reach curvature, we must fully close the foundation of flat spacetime, because warp concepts must respect local Lorentz invariance. Locally, spacetime always looks flat. No matter how curved the universe is globally, in a sufficiently small region, the laws of special relativity apply. This principle ensures that even in curved spacetime, nothing locally exceeds the speed of light. This local condition is central. It is what makes warp metrics subtle rather than contradictory. When physicists analyze proposed faster-than-light concepts, they check first whether any local observer sees superluminal motion. If the answer is yes, causality is broken. If the answer is no, then the geometry may permit unusual global effects while preserving local structure. Thus, the speed of light is both a limit and a structural constant. It defines how space and time interweave. It defines how intervals remain invariant. It defines how causal order is maintained, and it defines the conditions under which geometry must operate. Let us rest briefly in that understanding. The universe is not built from absolute space and ticking clocks. It is built from space-time intervals and light cones, from invariant geometry, from a constant that binds meters and seconds into one coherent fabric. When we say that the speed of light is the shape of reality, we mean precisely this. It is the conversion factor that turns temporal duration into spatial extension. It is the metric signature of space-time. It is embedded in the equations that describe electromagnetic waves, in the structure of Lorentz symmetry, in the energy-momentum relations of particles. Every field theory consistent with relativity respects this invariant speed. Even quantum field theory, the framework that describes particles as excitations of fields, preserves Lorentz symmetry at its foundation. The constancy of light speed is therefore not a superficial feature of classical electromagnetism. It is woven into the deepest layers of modern physics. And so, if humanity dreams of crossing interstellar distances in short spans of proper time, we must do so without violating the invariant interval, without tilting world lines outside the cone locally, without allowing information to outrun light in any infinitesimal neighborhood. This is the constraint, this is the discipline. And it is precisely why warp drive research focuses on metric engineering rather than propulsion. The geometry must change. The ship cannot outrun light. But perhaps the space-time in which the ship resides could evolve. Perhaps distances could contract not because the ship moves faster, but because the geometry between departure and destination shifts. But that possibility belongs to curved space-time. For now, we have completed the foundation. We have explored what the speed of light truly represents. We have seen why it is not merely a speed limit, but a structural constant. We have described Einstein's two postulates. We have examined time dilation and length contraction. We have clarified mass-energy equivalence. We have explained why nothing with rest mass can reach light speed. We have explored Lorentz transformations conceptually. We have defined light cones and causal structure. We have distinguished time-like, space-like, and light-like intervals. And we have seen why faster-than-light travel through space breaks causality. The geometry stands firm. It is calm. It is precise. And within its discipline, a deeper geometry waits. Let us continue gently. Now that the constancy of light has settled into the mind, now that the light cone stands steady, we can allow the idea of space-time itself to deepen. Space is not separate from time. Time is not separate from space. They are coordinates of a single four-dimensional structure. This insight did not emerge immediately from Einstein's work. It was Hermann Minkowski who clarified the geometry. He realized that the Lorentz transformations are not merely algebraic rules. They are rotations, but not ordinary rotations in three-dimensional space. They are rotations in a four-dimensional continuum with a different metric signature. In ordinary Euclidean space, the distance between 2 points is found by adding the squares of spatial differences and taking the square root. In space-time, the interval is found by subtracting the spatial part from the temporal part, scaled by the speed of light. This subtraction changes everything. It means time contributes differently than space. It means geometry has a mixed signature. It means the fabric of reality is not Euclidean. In this four-dimensional fabric, each object traces a world line. A world line is the complete history of an object through space-time, not just where it is, but when it is. A stationary object in space still moves through time. Its world line is vertical in a space-time diagram. An object moving through space tilts its world line. The faster it moves, the more it tilts toward the light cone. At light speed, the world line lies exactly on the cone. This is how we visualize motion in relativity. Motion is not simply displacement in space. It is orientation in space-time. Now consider proper time. Proper time is the time experienced along a world line. It is the time measured by a clock that travels with the object. Proper time is invariant. All observers agree on the proper time experienced along a specific world line. And this leads to one of the most subtle consequences of relativity. Different paths through space-time between two events can yield different amounts of proper time. Time becomes path-dependent. The famous twin paradox illustrates this. One twin remains on Earth. The other travels at high velocity and returns. The traveling twin experiences less proper time. The explanation lies not in acceleration alone, but in geometry. The two twins follow different world lines. One path through space-time is longer in proper time than the other. In flat space-time, inertial motion maximizes proper time. Acceleration changes the geometry of the path, thus aging becomes geometric. This may feel strange, but it is consistent and measurable. Atomic clocks flown on airplanes confirm it. Particles in accelerators confirm it. The geometry is not metaphorical, it is operational. Now we turn to simultaneity. In classical physics, events that occur at the same time for one observer occur at the same time for all observers. Relativity dissolves this assumption. Simultaneity becomes frame-dependent. Two events that appear simultaneous in one frame may occur in different temporal order in another, provided they are space-like separated. This does not violate causality, because space-like separated events cannot influence one another. But it changes our philosophical intuition. The universe does not possess a universal present. Instead, each observer has a slice of spacetime that defines their present. Different observers moving relative to one another slice spacetime differently. This leads to the block universe interpretation. In this view, past, present, and future all coexist within spacetime. The flow of time is not a feature of the four-dimensional manifold itself. It is a feature of consciousness moving along a world line. Spacetime simply is. Events are laid out geometrically. Causality constrains connections between them. But the manifold itself does not evolve. It contains all events. This interpretation remains debated, but it emerges naturally from the mathematics. Spacetime diagrams help make this intuition precise. On such diagrams, vertical axes represent time, horizontal axes represent space. Light rays form the 45-degree boundaries of the cone. World lines curve or tilt depending on motion. These diagrams reveal that what appears as motion in three-dimensional space is simply a path through four-dimensional geometry. Now let us revisit the invariant interval more slowly. The interval between two nearby events can be written conceptually as time difference squared times the speed of light squared minus space difference squared. This combination remains invariant under Lorentz transformations. Because it is invariant, it defines the metric of flat spacetime, and because it defines the metric, it defines geometry. Distance is not merely spatial separation. Distance in spacetime includes time. This is why geometry replaces force. In Newtonian mechanics, forces cause acceleration in space. In relativity, free motion is motion along straight lines in spacetime. Acceleration is deviation from inertial geodesics. Even in flat spacetime, geodesics are straight world lines. Curvature enters later, but the geometric view begins here. Massive particles move along time-like geodesics. Light moves along null geodesics. Space-like separations represent directions that no physical object can follow. Thus, motion is not a vector in space alone. It is a curve in spacetime. When we speak of velocity, we are describing the ratio of spatial displacement to temporal displacement along a world line. But the world line itself is the deeper object. This geometric view reshapes the concept of momentum. 4 momentum replaces 3 momentum. Energy and momentum become components of a single 4 vector. The invariant magnitude of this 4 vector equals the rest mass times the speed of light. Energy is not separate from momentum. They are unified in space-time structure. Even mass and energy unify through geometry. The relation energy squared equals momentum squared times the speed of light squared plus mass squared times the speed of light to the 4th emerges directly from Lorentz symmetry. This relation governs particle physics. It governs nuclear reactions. It governs the annihilation of matter into radiation, and it preserves the invariant interval in momentum space. We now see why geometry replaces force at a fundamental level, because the laws of physics must remain invariant under Lorentz transformations. This requirement is called Lorentz symmetry. Every fundamental interaction discovered so far respects it. Electromagnetism does, the weak interaction does, the strong interaction does. Even quantum field theory is constructed to preserve it. Thus, the four-dimensional fabric is not philosophical ornament. It is the scaffolding of physical law. And this scaffolding trains the mind. It trains us to abandon intuition based on separate space and time. It trains us to think in intervals and world lines. It trains us to recognize that velocity is geometric orientation. It trains us to understand that causality is encoded in cones. This training is essential because warp concepts operate at the level of the metric, not at the level of thrust, not at the level of fuel injection, but at the level of geometry. We must become comfortable thinking in 4 dimensions. We must become comfortable imagining that what we call distance might be altered by altering the metric. But altering the metric does not mean violating local Lorentz invariance. It means modifying the geometry globally while preserving local structure. That subtle distinction will matter profoundly. For now, we have completed the essential ideas. We have explored Minkowski's unification of space and time. We have explained proper time and world lines. We have described observer-dependent simultaneity. We have introduced the block universe interpretation. We have used space-time diagrams conceptually. We have defined the invariant interval. We have seen how geometry replaces force. And we have reframed motion as orientation within four-dimensional geometry. The mind has adjusted. It has loosened its grip on classical intuition. It has begun to see that reality is not a stage where events unfold, but a geometric structure where events reside. Rest in that structure. Let it feel steady, let it feel precise, because soon, geometry itself will begin to bend. Let us continue, gently. We have learned to see motion as geometry in flat spacetime. Now the fabric itself begins to respond. The first step toward this deeper insight is the equivalence principle. Imagine standing inside a small sealed elevator. You cannot see outside. If the elevator is at rest on the surface of a planet, you feel weight. If the elevator is accelerating upward in empty space at the same rate, you feel the same weight. There is no local experiment that distinguishes uniform acceleration from a uniform gravitational field. This simple observation led Einstein to a radical conclusion. Gravity is not a force in the Newtonian sense. It is indistinguishable from acceleration, locally. And if acceleration can be described geometrically as deviation from inertial motion, then perhaps gravity itself is geometry. Free fall becomes the key. A falling object does not feel a force. An astronaut in orbit feels weightless. In Newton's picture, gravity pulls constantly. In Einstein's picture, the astronaut follows the straightest possible path in curved spacetime. Weightlessness is not the absence of gravity. It is the absence of resistance to spacetime curvature. The failure of Newtonian intuition becomes clear when we examine light. Light has no rest mass. According to Newton's gravity, force depends on mass. Yet starlight bends near the sun. This bending was observed during a solar eclipse in 1919. The result matched Einstein's prediction. Light does not bend because a force pulls it. It bends because spacetime near the sun is curved. Light follows the straightest path available, a geodesic in curved geometry. To describe this curvature mathematically, Einstein developed the field equations. They are not simple equations, but conceptually they state something profound. Mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. On one side of the equations is geometry. On the other side is the distribution of matter and energy. The stress-energy tensor represents energy density, pressure, momentum flow. The curvature tensor represents how spacetime bends. The two are equal, scaled by fundamental constants. This equality is the heart of general relativity. But we can hold the idea without the full mathematics. Place a massive object in spacetime, the geometry adjusts. The adjustment is not an invisible force field. It is a change in the metric. Distances and durations are altered. Clocks tick differently near massive bodies. This has been measured. Clocks at higher altitude run slightly faster than clocks at sea level. This is gravitational time dilation. It is not mechanical, it is geometric. Now imagine two nearby free-falling particles released side by side. They drift toward one another if spacetime is curved. This convergence reflects tidal forces. It is not a force acting at a distance. It is the manifestation of curvature. In flat spacetime, parallel geodesics remain parallel. In curved spacetime, geodesics may converge or diverge. That is curvature. The curvature tensor encodes this precisely. It measures how much nearby geodesics deviate. Thus we reinterpret orbital motion. A planet orbiting a star is not continuously pulled inward. It is following a geodesic in curved spacetime. The curvature produced by the star shapes the planet's path. The planet's motion appears curved in space, but it is straight in spacetime. This shift in perspective is subtle and powerful. Straight lines can appear curved when projected into fewer dimensions. Just as a great circle on Earth appears curved on a flat map, a geodesic in 4 dimensions appears as orbital motion in 3. The universe itself becomes dynamic curvature. The Einstein field equations do not describe spacetime as rigid. They describe it as responsive. When matter moves, curvature changes. When curvature changes, matter responds. It is a dialogue between geometry and energy. Even empty space can curve. Gravitational waves propagate as ripples in curvature. These waves were directly detected in 2015. 2 black holes merged. Space-time itself vibrated. The detectors measured distortions smaller than a proton's width. This was not force, it was geometry oscillating. Black holes provide further insight. They are regions where curvature becomes extreme. The metric changes so drastically that not even light can escape. The boundary is called the event horizon. It is not a physical surface, it is a geometric condition. Paths that cross it inevitably move toward the singularity. Again, geometry governs motion. Mass and energy determine curvature. Curvature determines geodesics. Geodesics determine motion. This is the chain, and it is precise. Now let us consider the idea of energy itself shaping spacetime. Not only mass contributes, radiation contributes, pressure contributes, even vacuum energy contributes. All forms of stress energy influence curvature. This is essential because warp concepts rely on manipulating the stress energy distribution. They do not require new forces. They require particular curvature configurations. But curvature cannot be arbitrary. It must satisfy the field equations. Geometry is constrained by energy conditions. The equations do not permit any imagined bending. The bending must correspond to physically allowed stress energy. Thus, general relativity is flexible, but disciplined. It permits black holes, it permits expanding universes, it permits gravitational waves, it permits wormholes in principle. But each solution obeys precise mathematical relationships. The universe is not a chaotic sea of curvature. It is a lawful geometry. Even cosmology emerges from this framework. When we apply Einstein's equations to a uniform distribution of matter, we obtain the expanding universe solutions. The scale factor evolves in time. Space itself stretches. This expansion is not motion through space. It is evolution of the metric. Galaxies recede not because they fly through space at enormous speeds, but because the metric between them changes. This reinforces the central lesson. Motion is secondary. Geometry is primary. The field equations are local. They describe curvature at each point in spacetime, but the consequences are global. Entire universes can expand or contract. Black holes can form. Gravitational lenses can magnify distant galaxies, all because curvature governs geodesics. Now we pause and gather the ideas gently. We have explored the equivalence principle. We have reframed free fall as inertial motion in curved spacetime. We have seen why Newtonian force intuition fails at relativistic scales. We have introduced the conceptual meaning of the field equations. We have described how mass and energy shape spacetime. We have defined geodesics as straight paths in curved geometry. We have reinterpreted orbital motion geometrically, and we have recognized the universe as dynamic curvature. The mind has shifted again, first from space and time separate to spacetime unified, and now from flat spacetime to responsive curved spacetime. Rest here. Let the idea of geometry deepen, because once geometry is understood as dynamic, the idea of shaping geometry intentionally begins to feel less like fantasy and more like mathematics. Let us continue, slowly, carefully. There is a quiet fact about our universe that often surprises the mind. Distant galaxies are receding from us faster than light. This statement sounds impossible at first. You have just learned that nothing with rest mass can travel through space faster than light. Yet observations show that sufficiently distant galaxies recede at apparent speeds exceeding that limit. There is no contradiction. The key is to distinguish motion through space from expansion of space itself. In general relativity, spacetime is described by a metric, a rule that tells us how distances are measured. In cosmology, we often use a metric that assumes the universe is homogeneous and isotropic on large scales. This is known as the Friedmann-Lemaître-Robertson-Walker metric. Its essential feature is a time-dependent scale factor. The scale factor determines how distances between galaxies change with cosmic time. If the scale factor increases, space expands. When we say a galaxy recedes at a velocity greater than light speed, we do not mean it is moving through local space faster than light. Locally, every galaxy moves at subluminal speeds. But the distance between galaxies grows because the metric itself evolves. Imagine 2 points drawn on the surface of an inflating balloon. The points are not crawling across the surface stretches. As the balloon expands, the separation increases. If the balloon expands rapidly enough, distant points separate faster than light could traverse the surface. No local rule is broken. The expansion is global. This distinction between local velocity and global expansion is crucial. Special relativity governs local inertial frames. Within a sufficiently small region of spacetime, physics reduces to special relativity. No object outruns light locally, but over cosmological distances, the metric evolves. The recession velocity is not limited by special relativity because it is not a velocity through space. It is the growth of space itself. Edwin Hubble's observations in the early 20th century revealed that galaxies recede with a speed proportional to distance. The farther away a galaxy lies, the faster it recedes. At sufficiently large distances, the recession speed exceeds light speed. This does not produce causal paradoxes. Light emitted by such galaxies may never reach us if expansion outpaces the light's attempt to cross the intervening space. This defines a cosmic event horizon. But locally, physics remains intact. The scale factor evolves according to equations derived from general relativity. These are the Friedmann equations. They describe how the expansion rate depends on energy density, pressure, and curvature of the universe. Matter slows expansion. Radiation influences early evolution. Dark energy appears to accelerate expansion today. Dark energy is associated with vacuum energy, a constant energy density filling space. Its effect is repulsive on cosmological scales. The expansion accelerates, the geometry evolves, and in this evolving geometry, superluminal recession becomes natural. Now consider the early universe. Shortly after the Big Bang, the universe underwent a period of inflation. During inflation, the scale factor increased exponentially. Space doubled in size over incredibly short intervals. Tiny regions were stretched to astronomical scales. This rapid expansion smoothed out irregularities. It explains why distant regions of the universe share similar temperature. During inflation, the separation between regions grew faster than light. Again, no local laws were broken. Inflation demonstrates that superluminal expansion of space is not speculative. It is part of mainstream cosmological theory. The universe itself has already exhibited behavior that resembles warp motion. Not motion through space, but expansion of space. This realization is pivotal. If the universe can expand superluminally without violating relativity, then perhaps a localized region of space could be engineered to do something similar. The idea of a warp drive begins here, not by propelling a ship faster than light through space, but by modifying the metric around it. To understand this more deeply, imagine embedding a small region of space-time within a larger background. Suppose we create a localized region where the metric evolves differently. If space behind a spacecraft expands while space ahead contracts, the craft might effectively translate relative to distant observers. Locally, the craft remains at rest within its immediate spacetime. Globally, its position changes. The expansion of the universe demonstrates that geometry is not static. The metric is dynamical. The Friedmann-Lemaitre cosmology shows that large-scale geometry evolves according to energy content. Inflation shows that space can expand faster than light. Dark energy shows that expansion can accelerate. These phenomena provide conceptual permission. They show that relativity allows space-time to stretch and compress. The limitation remains local. No observer can measure light being outrun in their immediate frame. Causality remains intact locally. But globally, geometry can change in ways that appear to defy simple speed limits. This distinction between local and global behavior is subtle but essential. Consider a light beam emitted from Earth toward a distant galaxy. If the intervening space expands rapidly enough, the light may never reach the galaxy. Conversely, light emitted by distant galaxies beyond a certain horizon may never reach us. This horizon is not a wall. It is a geometric boundary defined by expansion rate. It emerges naturally from cosmological solutions. The lesson is gentle but profound. Relativity does not forbid superluminal separation. It forbids superluminal local motion. Space itself is permitted to expand at any rate determined by energy conditions and the field equations. Thus we arrive at a quiet insight. The universe already demonstrates that space-time can evolve faster than light. The metric expansion of space is real. Inflation was extreme. Cosmic acceleration continues today. These are not speculative ideas, they are supported by observation. If space can expand everywhere, perhaps it could expand selectively. If global expansion is driven by energy density, perhaps localized curvature could be engineered with an appropriate stress-energy configuration. The crucial distinction remains. Motion through space is constrained. Shaping space is constrained differently. Warp concepts explore the second possibility. They do not attempt to break the speed of light. They attempt to reshape the geometry through which motion occurs. This requires solving Einstein's equations with unusual stress-energy distributions. It requires energy densities that may not be readily available, but it does not violate the underlying structure of relativity. The Friedmann-Lemaitre cosmology and inflationary theory show that superluminal expansion is mathematically consistent. Thus, the universe itself provides precedent. The mind can rest in this realization. Relativity is not a prison of rigid limits. It is a geometry of profound flexibility, disciplined by precise equations. The expanding universe is proof that geometry can evolve. The challenge is whether geometry can be shaped locally, intentionally, and controllably. That question leads us deeper, towards specific metrics that attempt exactly this. In 1994, a Mexican theoretical physicist named Miguel Alcubierre asked a question that was both disciplined and daring. If general relativity allows spacetime to curve, could one design a specific curvature that mimics faster-than-light travel without violating relativity itself? He did not begin with engines. He did not begin with fuel. He began with geometry. Einstein's field equations relate curvature to energy and momentum. In simplified language, the equations say that matter and energy tell spacetime how to curve, and curvature tells matter how to move. Alcubierre chose not to search for an engine. He chose to search for a metric. A metric is the mathematical description of how distances and times are measured in a given spacetime. If one specifies a metric, one can compute the curvature associated with it. If the curvature is known, one can determine the required energy distribution that would produce it. Alcubierre proposed a metric in which a small, nearly flat region of spacetime, a bubble, is surrounded by a shell of curved spacetime. Inside the bubble, spacetime remains almost Minkowskian. That means locally flat. An observer inside would feel no acceleration, no crushing forces, no time distortion beyond ordinary relativistic effects. The spacecraft within the bubble would be locally at rest, but the bubble itself would move relative to distant observers. How? By expanding space behind it and contracting space ahead of it. Imagine space as a flexible fabric. Behind the bubble, distances grow. Ahead of the bubble, distances shrink. The bubble rides this gradient of curvature. From the perspective of distant observers, the bubble translates across space. Yet locally, the craft inside never exceeds the speed of light. Light inside the bubble behaves normally. Clocks tick normally. Physics locally respects special relativity. The apparent faster-than-light motion arises from global geometry. This is the crucial insight. Warp travel is not about moving through space faster than light. It is about manipulating the structure of space itself. Mathematically, Alcubierre defined a shape function that determines how the curvature transitions from flat interior to curved shell. The bubble has a finite radius. The curvature is concentrated in a surrounding region. The stress-energy tensor corresponding to this metric can be calculated. And here, a profound challenge appears. The required energy density in parts of the shell is negative. Negative energy density is not simply low energy. It is less than zero relative to the vacuum baseline. In classical physics, energy density is always positive. Mass contributes positive energy. Radiation contributes positive energy. But Alcubierre's metric requires regions where the energy density measured by certain observers is negative. This violates what are called energy conditions. In general relativity, energy conditions are assumptions about reasonable matter. The weak energy condition states that any observer measuring local energy density should find it non-negative. The null energy condition is related and constrains energy measured along light-like paths. The Alcubierre solution violates these classical conditions. This does not invalidate the mathematics. Einstein's equations permit such solutions, but they require exotic matter. Exotic matter is not antimatter. It is matter or energy with properties unlike ordinary substances. The original energy estimates were enormous. Early calculations suggested that the total negative energy required might exceed the mass energy of entire stars. To express this without numbers, imagine converting a massive celestial body entirely into energy. Even that might be insufficient. These estimates were discouraging, but the solution remained fascinating. For the first time, a rigorous metric within general relativity described effective superluminal travel without local violation of relativity. The spacecraft inside the bubble experiences free fall, no inertial forces, no time reversal. The bubble carries it along like a moving pocket of geometry. One subtle point is essential. From the viewpoint of someone inside the bubble, the destination appears to approach. Because space ahead contracts, distant points draw nearer. From the viewpoint of someone outside, the bubble traverses space rapidly. But no signal inside outruns light locally. Causality is preserved in local frames. However, global questions arise. Could such a bubble create horizons? Would communication across the bubble boundary be possible? These questions emerge naturally from the structure of the metric. The stress-energy tensor required by the solution reveals intense curvature gradients. The shell region contains enormous tidal stresses in the geometry. Even if negative energy were obtainable, controlling such distributions would demand precision beyond current understanding. Another challenge concerns energy scaling. The energy required grows with bubble size and velocity. A larger bubble requires more exotic energy. A higher effective velocity increases curvature intensity. The equations show that pushing the bubble faster intensifies the required negative energy density. Thus, the energy problem is not linear. It escalates rapidly. Nevertheless, Alcubierre's insight remains foundational. He demonstrated that faster-than-light effective motion is not forbidden by the structure of general relativity. The prohibition lies in local velocity. Warp geometry avoids local superluminal travel by reshaping spacetime. This was the mathematical birth of warp theory. After the publication of the metric, researchers began examining refinements. Could the energy be reduced? Could the shell thickness be modified? Could the shape function be optimized? One refinement was proposed by Chris van den Broek. He showed that by modifying the bubble geometry, shrinking the interior volume while maintaining an expanded exterior region, the total energy requirement could be dramatically reduced. The bubble interior could be tiny, while the external geometry appears large to distant observers. This clever manipulation reduced the integrated energy demand, though still requiring exotic matter. The lesson from these refinements is subtle. Warp geometry is not unique. There are families of possible metrics. Each metric corresponds to a different stress-energy configuration. Optimization becomes a geometric exercise. One searches for shapes that minimize exotic requirements while preserving desired motion. The mathematics of general relativity is flexible enough to allow such exploration. Yet every known superluminal warp solution to date requires violations of classical energy conditions. This remains the central obstacle. Still, the conceptual achievement stands. Alcubierre transformed speculative fiction into a problem in differential geometry. He showed that warp drive concepts can be framed rigorously. They can be analyzed quantitatively. They can be tested for internal consistency. They can be examined for stability and causality. This alone was profound. Before 1994, faster-than-light travel belonged largely to imagination. After the metric, it belonged to the mathematics of spacetime curvature. The energy problem did not negate the achievement. It clarified the difficulty. General relativity permits warp-like solutions. Quantum field theory may or may not permit the necessary energy configurations. The interplay between these domains defines the modern frontier. To summarize gently, Alcubierre proposed a spacetime metric with a flat interior bubble. The bubble is surrounded by a shell of curvature. Space expands behind and contracts ahead. The craft inside remains locally at rest. Effective faster-than-light motion emerges from global geometry. Relativity is not violated locally, but negative energy density is required, and the energy demands are immense. This is the foundation upon which all modern warp research rests. It is not fantasy. It is a solution to Einstein's equations. Its feasibility remains uncertain, but its existence reshaped how physicists think about the limits of motion. The universe already expands faster than light in places. Alcubierre showed that a localized expansion might, in principle, be engineered. The question then becomes, can the required curvature be redistributed, optimized, reduced? This leads naturally to later refinements. After the original warp metric was published, the equations did not disappear into silence. They became an invitation. If geometry allows such a configuration, can geometry also be optimized? Can curvature be redistributed? Can energy demands be reduced? These questions led to decades of theoretical refinement. Among the researchers who revisited the Alcubierre solution with renewed focus was Dr. Harold "Sonny" White. His approach did not reject the original metric. Instead, it asked whether the shape of the warp bubble could be modified in ways that reduce the total exotic energy requirement. The original solution assumed a thin shell of extreme curvature surrounding the bubble. In that configuration, the negative energy density spikes sharply at the boundary. White explored what would happen if the shell were thickened. A thicker shell spreads curvature over a broader region. Instead of concentrating distortion in an infinitesimally thin surface, the geometry becomes smoother. Mathematically, this changes the stress-energy distribution. When curvature is distributed more gradually, the peak energy density can decrease. Early refinements suggested that altering the radial profile of the shape function could reduce the total required energy by orders of magnitude. Orders of magnitude does not mean small. It means drastically reduced compared to astronomical baselines. Even then, the energy remains beyond current engineering capability. But the significance is conceptual. It shows that warp metrics are not fixed blueprints. They are families of solutions. White's investigations also emphasize numerical modeling. Einstein's equations are nonlinear. Small changes in geometry can produce large changes in stress-energy requirements. Computational tools allow researchers to simulate candidate metrics and compute their energy densities precisely. Instead of relying purely on analytic approximations, modern studies employ high-resolution grids to evaluate curvature invariance and stress-energy components. This transition marks a new phase in warp research. It is no longer merely symbolic manipulation. It is computational general relativity applied to speculative geometry. One refinement explored the concept of a toroidal energy distribution. Instead of a spherical shell, the energy density might be concentrated in a ring-like region. This ring surrounds the spacecraft along a specific axis. The curvature resembles a donut-shaped distortion. Such configurations alter how spacetime expands and contracts around the bubble. They also change the distribution of negative energy density. The goal remains consistent: reduce peak energy density. Maintain desired curvature, preserve mathematical consistency. Then, in more recent developments, White and collaborators introduced a concept that attracted renewed attention: a modular warp geometry. Instead of one continuous curvature shell, imagine discrete curvature regions arranged around a craft. These regions resemble segmented nacelles. Each nacelle is a localized curvature generator. Rather than a single spherical distortion, the warp geometry becomes distributed across separate modules. To describe this without equations, picture a spacecraft with two external pods positioned symmetrically. Each pod contributes a portion of the spacetime distortion. This configuration is sometimes referred to as the n=2 design. Here, n represents the number of curvature segments. In the n=2 configuration, two modules produce the necessary expansion and contraction fields. Now imagine adding a third module, symmetrically arranged. This becomes the n=3 configuration. Three curvature regions surround the craft in balanced geometry. Then imagine four modules arranged symmetrically around the hull. This becomes the n=4 configuration. Each nacelle contributes to the global curvature field. Instead of a continuous shell, spacetime distortion is discretized. Why does this matter? Because the stress-energy tensor depends sensitively on spatial gradients. If curvature can be distributed across multiple localized regions, peak energy density in any single location may be reduced. Isosurface modeling plays a role here. An isosurface is a three-dimensional surface representing points where a quantity has constant value. In warp modeling, isosurfaces can visualize regions of equal curvature magnitude or equal energy density. By examining these surfaces computationally, researchers can adjust nacelle placement and geometry to optimize curvature distribution. The modular approach allows geometric tuning. Instead of solving for one monolithic distortion, one can adjust parameters for each nacelle: spacing, orientation, relative intensity. All of these influence how the global curvature field emerges. Preliminary computational results suggest that segmentation may reduce peak negative energy density. The total integrated exotic energy may also shift depending on configuration. But crucially, the modular concept does not eliminate the need for exotic energy. It redistributes it. The negative energy regions remain necessary in classical general relativity. However, by separating exotic energy regions into discrete pods, theoretical control becomes conceptually clearer. One might imagine independent modulation of each nacelle's curvature field. Again, this remains theoretical. No experiment has generated such curvature fields. No laboratory apparatus has produced macroscopic negative energy densities required for warp metrics. But the mathematics is internally consistent. The segmented geometry satisfies Einstein's equations when the appropriate stress-energy distribution is specified. This is not speculative fiction. It is computational modeling grounded in general relativity. Another key advance enabling these refinements is improved numerical relativity. Modern algorithms solve Einstein's equations in discretized form. High-performance computing allows fine-grained analysis of candidate warp geometries. Researchers can simulate curvature invariance, energy density distributions, and stability properties. Stability is essential. A warp configuration that satisfies the equations at one instant may be dynamically unstable. Small perturbations could amplify. Curvature could diverge. Numerical tools allow simulation of such perturbations. They allow mapping of parameter spaces. They allow exploration beyond analytic approximations. White's work illustrates this computational transition. Warp theory is no longer confined to static metrics. It can be probed dynamically in simulations. The modular nacelle breakthrough highlights a broader principle. Geometry can be engineered mathematically. Space-time curvature can be sculpted in equations. Whether nature permits the required energy distributions remains open, but the geometric flexibility is real. To summarize gently, White revisited the Alcubierre metric and reduced energy estimates through shell thickening. He explored redistribution strategies. He emphasized numerical modeling. He introduced modular segmented nacelle geometries. The n equals 2 configuration uses 2 curvature modules. The n equals 3 configuration uses 3. The n equals 4 configuration uses 4 symmetrically arranged pods. Isosurface modeling visualizes curvature distribution. Segmentation redistributes space-time distortion. Peak negative energy density may decrease in optimized configurations. Exotic energy regions become separated into discrete controllable locations. The solutions remain theoretical. No experimental realization exists, but computational advances allow increasingly precise evaluation. The modular concept represents an evolution in warp geometry, not a finished engine, not a tested device, but a deeper understanding of how curvature might be shaped. This refinement does not guarantee feasibility. It does something equally important. It demonstrates that even extreme ideas can be approached with rigor, with equations, with simulation, with disciplined imagination. The equations of general relativity are elegant, but they are demanding. They do not permit geometry to bend without cost. Every curvature has a source. Every distortion of spacetime must be supported by energy and momentum. When the Alcubierre solution was first analyzed carefully, physicists noticed something extraordinary. The stress-energy tensor required to sustain the warp bubble contains regions of negative energy density. Not merely low energy, not empty space, but energy density below that of the vacuum. In classical physics, this seems impossible. Energy is positive, mass is positive. Matter resists acceleration. But in general relativity, energy conditions are assumptions, not laws. They are inequalities imposed on the stress-energy tensor to preserve physically reasonable behavior. One of these is called the weak energy condition. It states, in simple language, that for any observer moving through spacetime, the measured local energy density must be non-negative. Another is the null energy condition. It states that along any light-like direction, energy density must not be negative. These conditions ensure gravity behaves in familiar ways. They prevent exotic causal structures. They keep spacetime from folding into paradox. The Alcubierre metric violates these classical energy conditions. To expand space behind the bubble and contract it ahead, negative energy density must exist in specific regions. Without it, the curvature pattern cannot form. This is not a matter of technological limitation. It is embedded in the mathematics. So what does negative energy density actually mean? It does not mean energy with a minus sign attached casually. It means that the local energy measured by an observer is less than the vacuum baseline. In quantum field theory, the vacuum is not empty. It is a fluctuating sea of fields. Even in perfect emptiness, fields possess zero-point energy. They fluctuate, they oscillate, they cannot be completely still. These fluctuations give rise to observable phenomena. One of the most famous is the Casimir effect. When two uncharged conducting plates are placed very close together in a vacuum, the quantum vacuum modes between them become restricted. Only certain wavelengths can fit. Outside the plates, more modes are allowed. The result is a measurable force pushing the plates together. The vacuum between them has lower energy density than the vacuum outside. This is a real, experimentally verified effect, and it demonstrates something subtle. Quantum theory permits regions of reduced energy density relative to the vacuum. In other words, negative energy density is not purely fictional, but there is a difference between tiny laboratory effects and macroscopic spacetime engineering. The Casimir energy density is extremely small. It exists only over microscopic distances. Warp metrics, by contrast, require negative energy over macroscopic regions. Not nanometers, not microscopic separations, but volumes large enough to surround a spacecraft. The gulf between these scales is vast. Another constraint arises from quantum inequalities. These are mathematical limits derived from quantum field theory. They restrict how much negative energy can exist, for how long, and over what volume. In essence, quantum theory permits small violations of classical energy conditions, but only fleetingly. If negative energy appears in one region, it must be compensated elsewhere. Large accumulations appear forbidden. These inequalities act as safeguards against runaway exotic phenomena. They prevent arbitrary manipulation of vacuum energy. They constrain warp solutions severely. The Alcubierre configuration requires sustained negative energy density along the warp shell. Quantum inequalities suggest such sustained macroscopic distributions may be impossible. This is one of the deepest obstacles, not engineering, not materials science, but fundamental quantum constraints. Let us examine why ordinary matter cannot provide negative energy density. Matter consists of particles with positive rest mass. Mass contributes positively to energy density. Radiation contributes positively. Pressure contributes positively in most cases. To achieve negative energy density, one must rely on quantum field configurations. There is no classical substance with negative mass. Speculative concepts such as exotic matter with negative mass remain unobserved. Even if negative mass existed, its behavior under gravity would be profoundly unstable. It would repel positive mass. It would accelerate strangely. No evidence supports its existence. Thus, warp theory rests on quantum field effects, on vacuum engineering, on manipulating fluctuations. Yet vacuum energy itself is paradoxical. Quantum field theory predicts enormous vacuum energy density. Cosmological observations suggest the observed vacuum energy, often associated with dark energy, is small but non-zero. This mismatch is one of the greatest unsolved problems in physics. The vacuum is not fully understood. Warp theory touches this mystery. If vacuum energy could be controlled, perhaps negative regions could be engineered, but control is not comprehension. At present, we can measure subtle vacuum effects, not sculpt them at will. Another relevant concept is zero-point energy. Every quantum oscillator has a ground state energy. It cannot be reduced to zero. Even at absolute zero temperature, fields retain energy. Negative energy density arises when fluctuations are suppressed below this ground baseline. But suppression requires boundaries, configurations, constraints, not free-floating vacuum manipulation. Consider again the energy scale. Even optimistic estimates for refined warp metrics require energy equivalent to massive astronomical bodies. Although White's refinements reduced estimates dramatically compared to early calculations, the numbers remain immense. And these numbers refer to total integrated energy. Peak energy density remains problematic. Negative energy density must be concentrated in specific curvature regions. Segmentation redistributes it, but does not eliminate it. Quantum field theory does not provide a method to accumulate negative energy at will. The Casimir effect produces tiny amounts. Squeezed light states in quantum optics can produce local negative energy density for extremely short durations, but these are transient and microscopic. To scale such phenomena up by orders of magnitude, into meters, into seconds, into sustained curvature would require new physics. There is also a thermodynamic perspective. Energy conditions are closely related to entropy and stability. Violations could permit exotic phenomena such as traversable wormholes or time machines. Quantum inequalities may exist precisely to prevent such macroscopic violations. Nature appears to allow small fluctuations, but not global breakdown of causal structure. This brings us back to warp geometry. The mathematics allows it, but the stress-energy requirements challenge quantum constraints. White's modular segmentation attempts to reduce peak negative energy density. If peak density decreases sufficiently, perhaps quantum inequalities become less restrictive. But this remains speculative. Theoretical exploration continues. Some researchers investigate semi-classical gravity. In this framework, classical spacetime geometry interacts with quantum expectation values of the stress-energy tensor. Warp metrics are analyzed within this hybrid regime. Even here, negative energy remains bounded by quantum constraints. One might ask, could future quantum gravity theories alter these limits? We do not yet know. Quantum gravity remains incomplete. Until such a theory exists, warp energy requirements remain governed by known quantum field theory. And known quantum field theory is restrictive. There is also the issue of back reaction. If a region of negative energy density is generated, quantum fields respond, radiation may be produced, instabilities may arise, the geometry itself may amplify quantum fluctuations. These effects require detailed semi-classical analysis. They are not fully resolved. Thus, exotic matter is not merely an engineering challenge. It is a deep theoretical frontier. Warp research forces us to confront the limits of quantum vacuum physics. It tests the consistency between general relativity and quantum field theory. It highlights the tension between geometry and energy. The Casimir effect shows that vacuum energy can be manipulated slightly. Quantum inequalities show that manipulation is bounded. General relativity demands negative energy for warp geometry. The combination produces a delicate puzzle. This is where warp research becomes a probe of fundamental physics. Not simply a dream of faster travel, but an exploration of how quantum fields shape geometry. Perhaps future discoveries will reveal loopholes. Perhaps negative energy can be engineered in ways not yet imagined. Or perhaps quantum gravity will enforce even stricter prohibitions. At present, negative energy density exists in small, fleeting forms. Macroscopic accumulation appears impossible under known laws. Warp theory rests at this boundary, between allowed fluctuation and forbidden accumulation, between geometry's freedom and quantum constraint, and in that boundary, physics deepens. When spacetime is curved gently like around a star, its geometry is intuitive. Light bends, orbits form, clocks tick at slightly different rates. But when curvature becomes extreme, when geometry is engineered into a moving distortion, new structures appear. One of these structures is a horizon. A horizon is not a physical wall. It is not a membrane. It is a boundary in causal structure. It is a place beyond which signals cannot reach an observer. In black hole physics, the event horizon marks the region from which light cannot escape. Inside the horizon, all future directed paths lead inward. But horizons are not unique to black holes. They arise whenever space-time geometry restricts causal communication. Warp metrics possess this feature. In the Alcubierre solution, when the bubble moves at effective superluminal speed, a horizon forms at the front of the bubble. Light emitted from inside the bubble cannot reach that forward boundary. Signals cannot propagate to the leading edge. This is not a mechanical failure. It is geometric inevitability. Because the bubble front moves faster than light relative to the surrounding spacetime, no information from within can overtake it. The forward boundary becomes causally disconnected. The rear boundary behaves differently. Behind the bubble, expansion of space permits signals to move outward. But forward control becomes impossible once superluminal motion begins. This is known as the control paradox. To initiate a superluminal warp bubble, one must arrange its geometry in advance. But once it moves faster than light relative to the exterior, the occupants cannot modify the front edge. They cannot steer. They cannot stop the bubble by influencing its leading boundary. The geometry evolves beyond their causal reach. In practical terms, any trajectory would need to be pre-programmed. The stress-energy configuration would need to be arranged before departure. This introduces severe constraints. Navigation becomes fixed at launch. Dynamic maneuvering becomes problematic. Some theoretical refinements attempt to mitigate this issue. Subluminal warp solutions do not form horizons. If the bubble moves at less than light speed relative to exterior observers, signals can propagate to the front. But then effective faster-than-light travel is lost. The horizon emerges precisely when superluminal behavior appears. This reveals a deep connection between causality and warp geometry. General relativity preserves local light cones. No object locally exceeds light speed. Warp metrics maintain this locally, but globally, the bubble's motion relative to distant observers exceeds light speed. The horizon is the geometric expression of that global superluminality. Let us consider communication barriers more carefully. Imagine a signal emitted from inside the bubble toward the forward boundary. Inside the bubble, spacetime is approximately flat. The spacecraft is locally at rest, but the bubble wall moves relative to external space. If that relative speed exceeds light, no light signal from inside can catch up to the forward wall. Thus, control commands cannot reach the region of maximum contraction. The curvature distribution becomes autonomous. This is not an engineering flaw. It is a structural feature of the solution. The geometry contains regions that are space-like, separated from the interior. Causal disconnection is built into the metric. There are also stability concerns. Quantum fields propagating in curved spacetime can respond dramatically near horizons. In black hole physics, horizons are associated with particle production. Hawking radiation arises from quantum effects at the event horizon. Similarly, some analyses suggest warp horizons might produce radiation. Quantum vacuum fluctuations interacting with strong curvature gradients could generate energy flux. Whether this radiation would destabilize the bubble remains an open question. Semi-classical calculations indicate that horizon regions can accumulate stress. Back reaction from quantum fields could alter the geometry. If radiation accumulates at the front boundary, it might destabilize the warp shell. These effects are complex and not fully resolved. They require coupling quantum field theory with dynamic curved spacetime. Another paradox concerns chronology. If superluminal travel is possible even in one reference frame, closed time-like curves may arise in another. In special relativity, faster-than-light signals can be arranged to produce time loops. Warp metrics circumvent local faster-than-light motion, but global superluminal displacement can still threaten chronology. By combining two warp bubbles moving in opposite directions, one could theoretically construct a closed time-like curve. This would allow a traveler to return to their own past. Such solutions are mathematically permitted within certain parameter regimes. This raises deep concerns. If warp drives enable effective superluminal travel, they may also enable time travel. Time travel introduces paradoxes: the grandfather paradox, causal loops, logical contradictions. Physicist Stephen Hawking proposed the chronology protection conjecture. It suggests that quantum effects prevent macroscopic time machines. Perhaps vacuum fluctuations diverge near closed time-like curves. Perhaps space-time resists such constructions energetically. Warp metrics may encounter similar protective mechanisms. Even if classical solutions allow time loops, quantum corrections might destabilize them. Pre-programmed warp trajectories illustrate another limitation. Because forward control is causally blocked in superluminal configurations, the path must be defined before the bubble forms. External agents might need to construct the geometry. This suggests that warp travel cannot be piloted in the ordinary sense. It becomes more like launching a predefined geometric wave. Steering in real time would be impossible unless the bubble remains subluminal. There are also concerns about tidal forces. Inside the idealized warp bubble, curvature is negligible, but at the shell boundary, curvature gradients are extreme. If a spacecraft intersects unstable curvature regions, forces could be immense. Maintaining smooth transitions is mathematically delicate. White's modular segmentation redistributes curvature. It may smooth gradients, but horizon formation remains tied to superluminal motion. Another theoretical issue is the energy of the bubble walls. Negative energy density must be arranged in specific patterns. If these patterns fluctuate, the bubble might collapse. Dynamic stability analyses are ongoing. Numerical relativity simulations attempt to test perturbations. but fully time-dependent warp bubble stability remains unsolved. Consider also the issue of external observation. From the outside, the warp bubble appears as a moving region of distorted spacetime. Light rays are bent around it. Observers may see blue-shifted radiation ahead and red-shifted radiation behind. If the bubble stops abruptly, accumulated radiation at the front boundary could be released. Some studies suggest this could produce intense energy bursts. Whether this is inevitable depends on model assumptions, but it illustrates that horizons are not passive features. They shape energy flow. They influence stability. Let us return to the geometry itself. Horizons are surfaces where light cones tip. Inside the bubble, cones are upright. At the front boundary, cones tilt backward relative to the bubble interior. Signals attempting to move forward are swept backward by geometry. The forward region becomes unreachable. This tilting of light cones is a precise geometric description of causality. No physical barrier is needed. The structure of spacetime itself enforces separation. This is the essence of causal disconnection. Warp bubbles, therefore, are not merely energy distributions. They are global causal rearrangements. When superluminal displacement occurs, light cones must adjust, and when they adjust, horizons emerge. Control paradoxes are not incidental. They are woven into the geometry. To avoid them, one must remain subluminal. But to achieve effective faster-than-light travel, one must cross that threshold. Thus, the paradox is structural. The dream of superluminal geometry collides with causal order. Some researchers explore alternative metrics designed to avoid horizons. These typically restrict the bubble to subluminal speeds. They may reduce negative energy requirements, but they sacrifice the central feature of effective faster-than-light travel. It is as if nature draws a boundary. Below light speed, geometry can be engineered without severing causality. Above light speed, causality asserts itself through horizons, and in that assertion, control is lost. Warp research thus reveals another profound lesson. Geometry is not only about distance, it is about information, about what can influence what, about which events can be connected by signals. Horizons encode these limits. They mark the frontier of causal reach. If warp bubbles are ever realized, they must contend with these causal boundaries. Perhaps new physics will modify horizon behavior. Perhaps quantum gravity will soften singular boundaries. But within known general relativity, horizons are inevitable companions of superluminal geometry. They are not obstacles in the mechanical sense. They are the manifestation of spacetime's deepest rule. No signal outruns light locally. Even when space itself is sculpted, even when geometry is engineered, the causal fabric remains intact, and in preserving it, horizons appear. When a mathematical idea is first discovered, it is rarely the final form. The first solution opens a door, others walk through it. They examine its structure, they search for hidden symmetries. They ask whether assumptions can be relaxed, whether energy requirements can be softened, whether geometry can be rearranged. The Alcubierre metric was not the end of warp theory. It was the beginning. Very soon after its publication, researchers began exploring variations. They asked whether superluminal motion required the specific pattern of contraction ahead and expansion behind. They asked whether different coordinate choices could produce motion without explicit expansion of space. One of the most important alternatives was proposed by José Notario. Notario asked a simple question: what if the bubble does not expand space behind it and contract space ahead? What if instead, space-time inside the bubble moves like a flowing river without changing local volume? In the original Alcubierre formulation, space is stretched and squeezed. In Notario's approach, the geometry is constructed so that the expansion scalar is zero. In simpler words, space does not grow or shrink locally. Instead, it is rearranged through a shift vector field. The bubble becomes a region carried by a carefully designed flow of spacetime. This avoids explicit volume expansion and contraction. Why is this important? Because extreme expansion and contraction contribute to enormous stress energy requirements. By removing volumetric distortion, Notario's metric redistributes curvature differently. However, negative energy density remains necessary for superluminal motion. The energy conditions are still violated, but the geometry demonstrates something profound. Warp motion is not unique to one mathematical construction. There is flexibility in how spacetime may be shaped. Another important refinement was introduced by Chris van den Broek. His approach addressed the enormous energy problem in a different way. In early calculations, the energy required for an Alcubierre bubble large enough to carry a spacecraft was astronomical. Estimates suggested mass energy equivalent to entire stars, sometimes even more than the mass of the observable universe in extreme formulations. Van den Broek proposed modifying the geometry so that the interior region of flat space is extremely small from the outside, but expanded internally. Imagine a bubble whose exterior cross-section is microscopic, yet whose interior volume is large enough to hold a spacecraft. This is accomplished by warping spacetime in nested ways. The bubble throat becomes tiny externally, while internal geometry stretches. In principle, this dramatically reduces total negative energy requirements. Instead of curving a vast region of space, the distortion is concentrated into a thin layer surrounding a microscopic opening. Mathematically, the solution is consistent with Einstein's equations. Physically, it remains speculative. But the lesson is important. Energy requirements are sensitive to geometric design. Warp metrics are not rigid. They are families of solutions. Other researchers explored subluminal warp geometries. These do not attempt to exceed light speed relative to distant observers. Instead, they attempt to reduce inertial mass or effective acceleration. By shaping spacetime gently around a craft, one might reduce the energy cost of acceleration. Such models avoid horizon formation. They avoid severe causal paradoxes, but they do not enable effective faster-than-light displacement. They remain within relativistic speed limits. Still, these models are valuable. They test the flexibility of spacetime engineering. They explore what curvature manipulation can accomplish even without superluminal ambition. Numerical simulation tools have played a central role in these developments. Analytical solutions are elegant, but many realistic warp geometries cannot be solved in closed form. Instead, researchers use computational general relativity. They discretize spacetime into grids. They evolve Einstein's equations numerically. Stress-energy tensors are modeled as functions across computational domains. Energy densities, curvature scalars, and geodesic behavior are evaluated point by point. Open-source numerical relativity frameworks now exist. These tools were originally developed for simulating black hole mergers and gravitational waves, but they are adaptable. Warp geometries can be inserted as initial data. Their stability can be tested under perturbation. Researchers can vary parameters continuously: shell thickness, bubble radius, velocity profiles, segmentation patterns. The geometry responds in the simulation, curvature invariants are calculated, energy condition violations are mapped, light cone structures are visualized. This computational capacity did not exist in the early 1990s. Today, high-performance computing allows increasingly detailed modeling. Alternative warp geometries are therefore no longer purely symbolic expressions. They are computational objects. They can be stress-tested mathematically. Some researchers have explored warp solitons. These are self-stabilizing geometric waves. Rather than imposing curvature externally, the geometry would propagate as a stable solution of the field equations. Whether such solutions exist under realistic energy constraints remains uncertain, but the exploration continues. There are also studies of warp analogs in laboratory systems. Acoustic metrics in fluid dynamics mimic curved spacetime. Light propagation in metamaterials can simulate effective metrics. These analog systems do not produce real warp bubbles, but they test aspects of horizon formation and causal structure. In certain optical media, effective horizons can be created. Wave propagation mimics event horizon behavior. These experiments illuminate how geometry influences information flow. Even if warp drives remain theoretical, the study of alternative metrics deepens understanding of spacetime itself. Some alternative geometries aim not for superluminal travel, but for minimizing exotic matter requirements. Researchers investigate whether certain stress-energy distributions can reduce negative energy magnitude. Optimizing bubble wall thickness is one approach. If the shell is made thicker, curvature gradients decrease. Peak energy density drops. Total integrated energy may still be large, but local extremes are softened. Segmentation, as in modular designs, splits curvature into discrete regions. Alternative coordinate constructions may shift energy requirements into less extreme configurations. Each modification teaches something about the structure of Einstein's equations. They reveal how curvature couples to energy. They show that spacetime is malleable in theory, yet constrained by deep conditions. Computational general relativity also allows parameter sweeps. One can vary bubble velocity continuously, observe when horizons form, track when energy conditions are violated most severely, plot the relationship between bubble radius and total negative energy. Such numerical studies provide insight beyond analytic approximations. They reveal scaling laws. They show which geometric features are fundamental and which are artifacts of coordinate choice. Some open modeling frameworks allow public participation. Researchers share code. Curvature tensors are computed symbolically and numerically. Stress energy tensors are inserted into simulation grids. Geodesic tracing tools calculate particle trajectories. Even light rays can be propagated numerically through simulated warp geometries. This makes warp theory an active computational research area. It is not merely speculative fiction mathematics. It is part of the broader discipline of computational relativity. As alternative metrics accumulate, a pattern emerges. Superluminal solutions require negative energy. Horizon formation accompanies superluminal motion. Energy optimization reduces magnitude but does not eliminate violation. Subluminal solutions avoid severe paradoxes, but relinquish faster-than-light displacement. These patterns are not arbitrary. They reflect deep properties of spacetime. Alternative warp models are therefore like variations on a theme. Each explores a different harmonic of curvature. Each adjusts parameters. Each shifts energy distributions. Yet all remain bound by the same field equations. The Einstein equations are unforgiving. They allow remarkable geometric freedom, but demand consistency between curvature and stress energy. The exploration of alternative warp geometries is still evolving. It is a dialogue between mathematics and physics, between imagination and constraint, between ambition and conservation laws. Even if no warp drive is ever built, the study of these metrics sharpens understanding. It refines computational techniques. It deepens insight into global causal structure. It teaches us how geometry behaves under extreme distortion. And perhaps most importantly, it reminds us that physics is not static. Equations written more than a century ago still contain undiscovered possibilities, hidden solutions, subtle geometries, unexpected configurations. Alternative warp models are not promises of interstellar travel. They are explorations of the flexibility of space-time itself. They are exercises in disciplined imagination, and through them, we continue to learn what geometry permits and what it refuses. There comes a point when geometry itself begins to tremble, when curvature becomes so extreme that the smooth fabric of spacetime may no longer be smooth. General relativity treats spacetime as continuous, infinitely divisible, infinitely smooth. But quantum theory whispers something different. At sufficiently small scales, continuity may dissolve. The Planck scale marks that threshold. It is defined by combining three constants of nature: the speed of light, Planck's constant, and Newton's gravitational constant. From these emerges a length scale, approximately 1.6 times 10 to the negative 35 meters. Written in words, that is 1 divided by 10 followed by 35 zeros, meters, an almost unimaginably small distance. At this scale, quantum fluctuations of spacetime itself may become unavoidable. The Planck time is similarly small, roughly 5 times 10 to the negative 44 seconds. At durations shorter than this, the concept of classical time may lose meaning. If warp geometries require extreme curvature, then near their boundaries, one may approach regimes where classical general relativity is insufficient. Quantum gravity becomes relevant. Loop quantum gravity proposes that spacetime is not continuous. Instead, it may be composed of discrete quanta, tiny units of area and volume. These are not particles within space. They are the structure of space itself. In this view, geometry is quantized. Curvature cannot vary smoothly at arbitrarily small scales. There are minimal units. If this is true, then warp metrics relying on smooth continuous deformation may require reinterpretation. The bubble wall, with its steep gradients of curvature, might encounter quantum discreteness. Curvature tensors would no longer vary continuously. They would fluctuate in quantized steps. String theory offers a different perspective. In that framework, The fundamental objects are not point particles. They are one-dimensional strings. Their vibrational modes give rise to particles. Spacetime itself may emerge from deeper mathematical consistency conditions. Extra dimensions are often invoked, compactified dimensions beyond ordinary perception. If spacetime emerges from string interactions, then warp geometries may correspond to exotic string configurations, or they may be forbidden by consistency constraints. String theory has produced hints of holography. The holographic principle suggests that the information content of a region of space is proportional not to its volume, but to its boundary area. This emerged from studies of black hole entropy. If spacetime obeys holographic limits, then extreme curvature regions may be bounded by information constraints. A warp bubble wall, with its concentration of energy density, may be limited by holographic entropy bounds. Quantum gravity also introduces the possibility that spacetime is emergent, not fundamental. Some approaches suggest spacetime arises from entanglement patterns in deeper quantum systems. Geometry becomes a manifestation of information relationships. If that is true, then warping space may correspond to reorganizing entanglement. Energy conditions might reflect constraints on information flow. In such a framework, negative energy density could correspond to unusual entanglement configurations. Whether such configurations are physically realizable remains unknown. The Planck scale also implies limits on curvature. Classical general relativity allows arbitrarily high curvature, but quantum corrections may regularize singularities. Black hole singularities are expected to be replaced by finite quantum geometries. If warp bubble walls attempt to approach extreme curvature, quantum gravitational corrections could alter the solution. Some studies explore semi-classical gravity. In this regime, quantum fields propagate on classical curved backgrounds. The stress-energy tensor includes quantum expectation values. Vacuum polarization effects appear. Back reaction modifies curvature. In warp metrics, quantum field effects near horizons could generate radiation, analogous to Hawking radiation. Whether this destabilizes the bubble is unclear. Quantum inequalities impose further constraints. These inequalities limit how much negative energy can exist for how long. They arise from quantum field theory in curved spacetime. They suggest that negative energy must be accompanied by compensating positive energy, and that its duration is constrained by magnitude. If warp drives require sustained macroscopic negative energy, quantum inequalities present a serious obstacle. Emergent spacetime hypotheses add another layer. Some physicists propose that spacetime geometry arises from tensor networks or quantum error-correcting codes. In such pictures, curvature is a manifestation of entanglement structure. Warping geometry may correspond to modifying connectivity patterns, but these underlying systems may have stability constraints. Not every connectivity pattern is allowed. Thus, warp geometries could be mathematically consistent in classical theory, yet incompatible with deeper emergent rules. The Planck energy scale is enormous, roughly 1.2 times 10 to the 19 billion electron volts. In everyday units, far beyond laboratory capabilities. If warp bubbles require approaching Planck scale curvature, experimental realization becomes implausible. Yet the interplay between warp metrics and quantum gravity remains largely unexplored. Most warp studies remain classical. Quantum gravity is incomplete. We do not yet possess a full theory unifying relativity and quantum mechanics. Therefore, warp theory sits at a boundary. It is allowed by classical equations, yet challenged by quantum considerations. Perhaps quantum gravity will prohibit macroscopic negative energy. Perhaps it will reveal mechanisms for stabilizing curvature. Perhaps spacetime discreteness will regularize bubble walls. Or perhaps the Planck scale simply marks a domain beyond engineering. Even if warp travel is never realized, studying its compatibility with quantum gravity sharpens both fields. It forces questions. Is spacetime continuous or discrete? Are energy conditions fundamental or emergent? Is geometry primary or derivative of quantum information? Warp research therefore intersects with the deepest puzzles in physics. Not merely propulsion, but ontology. What is spacetime made of? Is it substance or relationship? The Planck scale remains distant from experiment, yet theoretical exploration continues. Mathematical consistency is a guide. If a warp metric violates deep quantum principles, it may be ruled out. If it survives semi-classical scrutiny, it becomes more intriguing. At the boundary of quantum gravity, certainty fades. Speculation grows careful. The geometry of possibility narrows, but does not vanish. Spacetime may be granular. It may be woven from discrete loops. It may be holographic. It may be emergent from entanglement. Whatever its nature, warp theory touches its edges. It presses against the limits of smoothness. It asks whether geometry can be engineered at scales approaching fundamental discreteness. And in doing so, it reminds us that even space and time themselves may not be final. Space-time is not merely a stage, it is a structure of cause and effect. Every event sits inside a light cone. Every moment is shaped by what can influence it and what it can influence in return. Causality is geometry. In special relativity, the light cone divides space-time into regions. Inside the cone, events can be connected by signals moving slower than light. On the surface of the cone, events are connected by light itself. Outside the cone, events are space-like, separated. No influence can travel between them without exceeding the speed of light. This structure protects temporal order. Cause precedes effect. No observer sees a contradiction. Warp metrics disturb this simplicity, because they allow effective faster-than-light travel relative to distant observers, not locally, but globally. If a warp bubble moves superluminally between two distant stars, it may arrive before a light signal would, and in certain reference frames, arrival could appear to precede departure. This does not immediately produce a paradox, but under specific configurations, it can. Closed time-like curves are paths through spacetime that return to their starting point in time. They are solutions permitted by certain metrics. If an object travels along such a curve, it could encounter its own past. General relativity does not forbid these solutions outright. The mathematics allows them. Warp metrics combined with relative motion can create similar possibilities. Imagine two observers moving relative to one another. If each possesses a warp capability, carefully orchestrated journeys might create loops in time. The geometry bends in such a way that departure and arrival events become cyclic. This opens the door to paradox. The grandfather paradox is often cited. An individual travels to the past and prevents their own existence. Logical contradiction emerges. Tachyon paradoxes offer another example. Hypothetical, faster-than-light particles, called tachyons, would allow signals to propagate backward in time in some frames. Messages could be received before being sent. Responses could prevent the original transmission. Causality fractures. Warp travel may avoid local light speed violation, yet still create global causal loops. This is because relativity links space and time. Superluminal effective travel corresponds to time-like path deformation. The structure of simultaneity changes between observers. What is future in one frame may be past in another. Chronology protection is a proposed principle suggesting that nature forbids macroscopic time loops. The conjecture was articulated by Stephen Hawking. He proposed that quantum effects may intervene before closed time-like curves can form. Vacuum fluctuations near the formation of such curves might grow without bound. Energy densities could diverge. The geometry would destabilize. Time loops would self-destruct before becoming usable. This idea is not proven, but semi-classical calculations indicate that quantum stress energy may diverge near chronology horizons. A chronology horizon is the boundary beyond which closed time-like curves would appear. As one approaches such a boundary, quantum fields may accumulate infinite energy density. If true, warp metrics that permit time loops may be unstable. The warp bubble horizon itself introduces causal complexity. Signals cannot propagate from inside to the front edge if the bubble moves faster than light relative to distant observers. This creates effective horizons similar to those of black holes. Control becomes subtle. If the front of the bubble is causally disconnected from its interior, how can it be steered? Some analyses suggest that the bubble must be pre-programmed, trajectory determined in advance. Otherwise, feedback from the front boundary cannot reach the interior in time. This connects to causality constraints. If control signals cannot propagate forward within the bubble, then dynamic steering may be impossible. Furthermore, if a bubble permits round-trip superluminal travel between moving observers, closed time-like curves become possible. Two warp trajectories in opposite directions could combine into a temporal loop. This does not require exotic machinery beyond warp itself. It arises from relativity's geometry. Therefore, even if negative energy could be engineered, causal stability remains a profound concern. Some researchers explore restricted warp metrics that are strictly subluminal. These avoid time loop formation. They still involve curvature engineering but do not exceed light speed relative to distant observers. Such geometries preserve global causality, but they sacrifice interstellar shortcuts. Chronology protection may not forbid all warp solutions. It may forbid only those enabling closed time-like curves. The distinction is subtle. Superluminal effective travel does not automatically imply time travel. It depends on configuration and relative motion. Yet any superluminal mechanism invites scrutiny. Causality is deeply embedded in physical law. Thermodynamics presumes it. Quantum theory presumes it. Statistical mechanics presumes temporal ordering. If warp geometries undermine causality, they challenge the coherence of physics itself. Some theoretical work suggests that consistent histories in quantum mechanics may exclude paradoxical loops. Probability amplitudes might interfere destructively for inconsistent timelines. Nature may self-select consistent solutions. Alternatively, time loops may exist. But paradoxes may resolve through self-consistency. The Novikov self-consistency principle proposes that events along closed time-like curves are globally consistent. One cannot change the past because the past already includes the time traveler's actions. Yet this is philosophical as much as physical. Experimental evidence remains absent. In practical warp research, chronology concerns remain theoretical. Energy requirements dominate engineering discussion. But at the conceptual level, causality defines legitimacy. If warp travel cannot avoid chronology violation, then deeper principles may prohibit it. If a geometry is mathematically consistent yet physically unrealizable, chronology protection may be the reason. Even without paradox, horizons complicate stability. Energy accumulation at bubble boundaries may radiate. Particle production analogous to Hawking radiation may occur. Quantum back reaction may destabilize the metric. These effects require detailed semi-classical calculation. They remain open questions. Thus, warp theory stands at the intersection of geometry and causality. It tests whether spacetime curvature can be engineered without fracturing temporal order. It challenges us to ask whether the universe permits shortcuts, or whether causal structure is absolute. Perhaps causality is not merely a feature of spacetime. Perhaps it is a principle guarding consistency, a symmetry of logic embedded in geometry. Warp research does not yet answer this, but it clarifies the stakes. To bend space is one thing, to bend time is another, and in relativity, the two are inseparable. When physicists write down a warp metric, they are not building a machine, they are building a question written in geometry, a question written in curvature tensors, in stress energy distributions, in the quiet language of differential equations. And the question is simple. Does the structure of spacetime permit shortcuts, or does it protect its own order? The study of warp geometries has never been only about propulsion. It has always been about understanding the boundaries of general relativity. When Miguel Alcubierre proposed a spacetime solution in 1994, he did not claim engineering feasibility. He demonstrated that Einstein's field equations admit a metric in which a compact region of flat spacetime is carried by surrounding curvature. This alone was profound. It revealed that faster-than-light effective travel is not immediately excluded by relativity if the motion is geometric rather than local. The discovery shifted perspective. It reminded physicists that equations often contain more possibilities than intuition suggests. Warp research teaches humility. The Einstein field equations are compact when written in symbolic form, yet their solution space is vast. Black holes were once exotic mathematical curiosities. Now they are observed. Gravitational waves were once theoretical perturbations. Now they are detected routinely. Mathematics precedes instrumentation. Warp metrics exist as exact solutions whether or not nature allows their realization. That distinction is important. Mathematical consistency does not guarantee physical feasibility, but it forces careful thinking. Warp research compels physicists to examine energy conditions, the weak energy condition, the null energy condition, the strong energy condition. These are assumptions about the behavior of matter and energy. They are not derived from geometry alone. They are additional constraints reflecting observed physics. Warp metrics violate some of these conditions. Specifically, they require negative energy density in certain regions. This challenges classical intuition, but it also illuminates the limits of that intuition. Quantum field theory already permits local violations of classical energy conditions. The Casimir effect demonstrates measurable negative energy density between conducting plates separated by microscopic distances. Quantum inequalities constrain magnitude and duration, but they do not forbid negativity entirely. Thus, warp research bridges general relativity and quantum theory. It reveals where classical geometry meets quantum vacuum fluctuations. It exposes tensions between macroscopic curvature and microscopic field behavior. In doing so, it maps the frontier between two great pillars of physics. Warp studies also deepen our understanding of numerical relativity. The Einstein field equations are nonlinear partial differential equations. Exact analytic solutions are rare. Most realistic geometries require computational methods. Modern warp refinements, including those explored by Dr. Harold Sonny White, depend on numerical modeling of stress-energy distributions. By simulating segmented curvature regions, researchers investigate how energy density might be redistributed. Isosurface modeling visualizes regions of positive and negative curvature. Computational tools allow exploration of thick shell configurations, modular geometries, and segmented nacelle concepts. Even if warp propulsion remains unrealized, the computational techniques developed are valuable. They refine numerical methods. They sharpen understanding of how curvature behaves under complex conditions. They improve simulation frameworks applicable to astrophysics and cosmology. Warp research therefore advances mathematics itself. It demands precision in tensor analysis. It encourages clarity in causal structure interpretation. It stimulates careful consideration of global topology. Questions about event horizons and chronology protection arise naturally. Closed time-like curves are not merely narrative devices. They are permitted by certain exact solutions. Exploring whether nature forbids them requires deep theoretical insight. The chronology protection conjecture suggests that quantum back reaction may prevent time loops. Whether this is true remains unsettled, but the investigation sharpens understanding of semi-classical gravity. It forces examination of how quantum fields behave in curved backgrounds. Warp theory therefore acts as a stress test for physics. It probes consistency, it identifies where equations strain, it reveals which assumptions are empirical and which are mathematical necessities. Beyond physics, warp research has philosophical resonance. It asks whether limits are fundamental or emergent. Is the speed of light an unbreakable barrier or a local constraint within a deeper geometric freedom? If space can expand faster than light in cosmology, as during inflation, then superluminal expansion is not forbidden in principle. The distinction lies between local motion and global metric evolution. Understanding that distinction transforms intuition. Warp research teaches that velocity is not always what it seems. It encourages thinking in terms of invariance rather than appearances. Proper time, invariant intervals, curvature scalars, these are deeper measures than coordinate speed. Philosophically, warp theory embodies disciplined imagination. Science fiction imagines starships leaping between stars. Physics asks whether geometry permits such leaps. Imagination proposes, mathematics disposes. Between them lies inquiry. Warp studies illustrate that curiosity can be rigorous. One can ask bold questions while remaining grounded in equations. This is the essence of theoretical physics. Speculation guided by consistency. Dreams filtered through tensor calculus. There is also a lesson in scale. Energy estimates for warp metrics have often been enormous. Early calculations suggested requirements comparable to the mass energy of entire planets. Later refinements reduced estimates dramatically, but still far beyond current capability. This teaches proportion. It reminds us that nature's geometry is vast. Curving spacetime is not trivial. Mass energy equivalence relates energy to curvature. To engineer curvature on macroscopic scales requires extraordinary resources. Yet the act of calculating those requirements refines understanding of stress-energy tensors. It clarifies how geometry responds to distribution. Warp research also reinforces the unity of physics. Special relativity defines causal structure. General relativity defines dynamic curvature. Quantum field theory defines vacuum fluctuations. Cosmology demonstrates superluminal expansion of space. Quantum gravity seeks to reconcile them all. Warp metrics sit at their intersection. They cannot be considered in isolation. Every aspect connects. Causality, energy conditions, quantum inequalities, horizons, all converge. In exploring warp geometry, physicists confront the coherence of the entire framework. This coherence is beautiful. It is not decorative beauty, but structural elegance. Equations constrain possibility. Symmetry shapes law. Geometry encodes interaction. Warp research is not an attempt to violate physics. It is an attempt to understand its flexibility, to see how far curvature can bend before it breaks. Perhaps practical warp propulsion will never exist. Perhaps negative energy cannot be accumulated macroscopically. Perhaps chronology protection prevents paradox. Even so, the investigation remains meaningful. It clarifies boundaries, it strengthens theory, it illuminates what is permitted and what is not. Science advances as much by mapping impossibility as by achieving possibility. Every constraint discovered is knowledge gained. Every prohibition understood is insight secured. Warp theory reveals that the universe is not rigidly intuitive. It reveals that limits often arise from deep structural relationships. It reveals that geometry is the language of reality. And that language can be explored, even when its engineering translation remains distant. In contemplating warped spacetime, we contemplate the flexibility of existence itself. We contemplate whether distance is absolute or negotiable through curvature. We contemplate whether causality is inviolable or delicately protected. These reflections are not escapism. They are meditations grounded in mathematics. They expand perspective. They cultivate intellectual patience. They encourage comfort with uncertainty. And perhaps that is the most enduring lesson. Warp research is a mirror of human curiosity. We look at the stars and we ask whether geometry might carry us there. We look at equations and we ask what they allow. The answers are subtle. They unfold slowly through calculation, through debate, through refinement. This process itself is valuable. It demonstrates that wonder and rigor are not opposites. They are partners. Theoretical physics is the art of disciplined wonder. Warp metrics are one expression of that art. They may never power a starship, but they power understanding. They remind us that the universe is structured, and that within that structure lies possibility. Possibility bounded by logic, yet expansive in imagination. And in exploring those bounds, we learn not only about spacetime, but about the nature of inquiry itself. Spacetime does not rush, it does not strain. It does not announce its structure, it simply is. A four-dimensional continuum, woven from intervals, shaped by energy, guided by geometry. Across this quiet fabric, stars ignite, galaxies rotate, black holes curve light into arcs. The same equations that describe a falling apple describe the expansion of the universe. The same curvature that bends a beam of light governs the orbit of planets. In this vast structure, warp metrics are not intrusions. They are possibilities written in the margins of general relativity. They are solutions permitted by equations that already describe our cosmos. To contemplate warped spacetime is not to escape reality. It is to examine it carefully. The Einstein field equations relate curvature to energy and momentum. They do not specify which distributions must occur. They describe how geometry responds when energy is present. When researchers ask whether a bubble of flat spacetime can ride within a moving distortion, they are asking how flexible curvature may be. They are asking whether geometry can be engineered, or whether its elasticity is tightly bound. In cosmology, space itself expands. During the early universe, inflation stretched spacetime at an extraordinary rate. Distant regions separated faster than light could traverse static space. Yet locally, nothing outran light. This distinction between local motion and global expansion reshaped understanding. It revealed that the speed of light is a limit within spacetime, not necessarily a limit of spacetime. Warp research draws upon this insight. If space can stretch, if metrics can evolve, then perhaps geometry can be configured in subtle ways. Whether such configurations are physically realizable remains unknown. But the investigation illuminates structure. It reveals that the universe is not defined by naive intuition. It is defined by invariance, the invariant interval, proper time, curvature scalars. These quantities remain constant across frames. They are the anchors of understanding. Throughout this exploration, a pattern emerges. Every bold proposal must pass through consistency. Energy conditions constrain stress-energy tensors. Quantum inequalities restrict negative energy accumulation. Causal structure guards chronology. Event horizons define boundaries of influence. No equation stands alone. Each connects to the rest of physics. This interconnection is itself profound. It suggests that reality is coherent. Constraints discovered in one domain echo in another. Quantum vacuum fluctuations influence curvature possibilities. Causal geometry influences allowable matter distributions. Speculation is disciplined by structure, and that discipline is not limiting, it is clarifying. The pursuit of warp geometries has required advances in numerical modeling. Nonlinear equations resist simple solutions. Computational relativity enables visualization of curvature distributions. Isosurfaces reveal where spacetime bends. Segmented configurations redistribute stress energy. Optimization techniques minimize peak densities. Even if warp propulsion remains theoretical, the computational tools developed enrich astrophysics and gravitational wave modeling. Knowledge expands regardless of outcome. At the frontier of physics, questions about quantum gravity arise. At extremely small scales, classical geometry may dissolve into discrete structure. Loop quantum gravity suggests quantized areas and volumes. String theory proposes vibrating fundamental entities. The holographic principle hints that information content may scale with surface area rather than volume. Whether spacetime is fundamental or emergent from deeper degrees of freedom remains unsettled. Warp research intersects these mysteries. If spacetime can be shaped macroscopically, what is its microscopic texture? Does negative energy correspond to subtle rearrangements of vacuum states? Are there deeper conservation principles yet undiscovered? Such questions extend beyond propulsion. They probe the ontology of geometry itself. Causality remains central. Closed time-like curves appear in certain mathematical solutions, but nature may protect chronology through quantum back reaction. The chronology protection conjecture suggests that vacuum fluctuations grow large near potential time loops, preventing their formation. If this is true, then the universe contains self-consistency safeguards. Limits are not arbitrary, they are woven into structure. In contemplating warp metrics, we confront both possibility and restraint. Possibility, because equations permit more than intuition first suggests. Restraint, because physical conditions narrow those permissions. This duality is instructive. It mirrors the broader human condition. Curiosity pushes outward. Reality answers with boundaries. Within those boundaries, understanding deepens. The philosophical value of this journey lies not in engineering outcomes, but in perspective. To ask whether space can be warped is to take geometry seriously. To treat spacetime not as a passive backdrop, but as dynamic structure. This shift is transformative. It reframes motion, distance, time as properties of curvature rather than absolutes. The speed of light becomes the geometry of causality. Gravity becomes the bending of world lines. Expansion becomes metric evolution. Such reinterpretations are quiet revolutions. They do not shout, they reorganize understanding. Warp theory also cultivates humility. The energies required appear immense. Negative energy remains constrained by quantum inequalities. Event horizons complicate control. These obstacles are not failures, they are insights. They reveal how tightly woven physical law is. They demonstrate that space-time resists casual manipulation. And yet, even in resistance, there is beauty. Because resistance reveals structure, and structure reveals coherence. In the end, whether humanity ever bends space-time intentionally is secondary. What endures is the clarity gained in asking, the willingness to explore mathematics fully, the courage to test assumptions, the patience to accept limits when they arise. Across billions of light years, galaxies drift apart as the universe expands. Within atoms, quantum fields fluctuate in restless activity. Between them, curvature connects scale to scale. We inhabit this continuum. We measure it, we model it, we question it, and through questioning we become more aware of its depth. Space-time can be imagined as an ocean, not turbulent but vast. Its waves are gravitational disturbances, its currents are expansions and contractions, its surface is not separate from its depths. All is geometry. To rest in that realization is calming. There is no urgency in equations. They describe what is. They do not demand. They reveal. As thought slows, as analysis settles, one sees that curiosity itself is peaceful. It does not require conquest. It requires attention. Warp theory is attention applied to possibility, a careful unfolding of metric structure, a respectful dialogue with general relativity. And perhaps that is the quiet lesson. The universe invites exploration, but only through coherence, through consistency, through mathematics. In that invitation, there is wonder, not the loud wonder of spectacle, but the steady wonder of comprehension. Space-time remains vast. Its curvature continues to guide galaxies. Its invariants continue to define causality. Its expansion continues without haste, and within it, questions continue to arise. Each question bends thought slightly. Each answer straightens it again. This rhythm is the rhythm of science, a rhythm without sound, yet deeply resonant. Rest in that rhythm. Rest in geometry. Rest in the quiet understanding that reality is structured, coherent, and open to inquiry. The stars remain distant, but understanding brings them nearer, not by shortening space, but by deepening perception. And that is a journey without violation of light, without distortion of causality, yet infinite in reach.